Section 11.7, strategies for testing series. Here we're not going to learn like a new test, but as you notice, we recalled all the exams on the board today. I just want to list them out one more time here. But the way I'm going to list them out is that's my recommended way when you approach series to test a series conversion divergence. Where do you start? We always start with the simple ones. Like don't do integral tests, for example, even if you think, oh, it's going to work. You start with simple ones. And as you practice more and more, some of the tests will take you like 5 seconds or 10 seconds, and you just keep moving on. So when you walk into taking an exam, you can write all these tests on the first page on the right side or the last page. And then you go through, while you're doing testing the series, you can go through the process of elimination. You know, you try. The first one I would recommend you look at and see, can I use the p-test? P-test is like the easiest one to look at. Say, okay, is p bigger than 1, less than 1, you know, like, or equal to 1? Then you can tell if it converges or diverges. The next test is the divergence test. Again, some people call it the n-term test, where you only have to find the limit of an as n goes to infinity. And if you think, oh, this doesn't work, I need to try something different, we recommend the geometric series test. We abbreviate with GST. Because in the geometric series test, usually you just plug in n values, n1, n2, n3, and then you would see that you find the pattern. Oh, okay, this is R, and check if R between -1 and 1 or not. Then based on that, you can tell if it converges or diverges. The next set is those related to conversion test and limit conversion test. One thing to keep in mind, it's easier to do limit conversion test than conversion test. So you can try the limit conversion test. That's provided, I'm going to call it LCT, provided you don't know if the conversion test is going to work or not. Then the conversion test, CT. If you think there is like factorial in the sequence, factorial, or a number to n, factorial or number to n, we use ratio test. If you see the nth, you know, the nth root or something to n or n square, that's where we use the root test. If you see there is like -1 to some power, that's where we use the AST, alternating series test. Alternating series test, AST. Also, keep in mind the last one that we use is the integral test. We keep the integral test till the end because it has a lot of conditions that you need to verify, continuity, decreasing, and positive terms. And not only that, when you go through the integral, there will be a lot of work to do because it's an improper integral. You have to rewrite it as a limit and then integrate and pass the limit. Sometimes you have to do L'Hopital's rule. So there's a lot of work involved. On the top of listing out the exams, keep in mind the sums. Usually in the sum, we have the integral, or not the integral, sorry, the geometric series. They can have a sum. And the other one is the telescoping series. So sums usually come from either telescoping or geometric. Now, on a test, what could that be is they could ask you, you know, move on. So let's look at an example. So you might be asked to test for conversions or divergence. Okay, and we take into account some series might converge conditionally absolutely or diverges. N plus 1, 5 to the n over n times 3 to the 2n as n runs from 1 to infinity. So when I look at a question like this, I think that's a little bit difficult for me. What am I going to do? I need to decide. That's not a p-test for sure. So you go through the list, you make it as a column. You cross out the p-test. Is that nth test? Like if you pass n goes to infinity, that's going to be a lot of work. You have to do, you're going to get indeterminate problem. That's not a good option. You cross it out. Then you run through the list, down the list. If you want to use comparison or limit comparison, it's not going to be easy to compare this to another test. But what is the key element here is when I see a number raised to n, like this, or this, when I see something like that, that tells me use ratio test. Use ratio test. So I'm going to use ratio test. And I'm going to recall from the previous section what the ratio test is. So recall. The ratio test says you find the limit as n goes to infinity of a sub n plus 1 all divided by a sub n. It can't be the other way around. It has to be a sub n plus 1 over a sub n. And if the limit, this limit, when you calculate this, is L, depending on the value of L, you could get, if it's bigger than 1 or infinity, then it diverges. If it's less than 1, converges. If it's equal to 1, inconclusive. Inconclusive means we cannot conclude anything about if it converges or diverges. In this case, what we have to do is try a different test. So from the given problem, I can see what an is. It's the n plus 1 times 5 to the n over n times 3 to the 2n. From this, I can replace every n with n plus 1. So that gives me n plus 2, 5 to the n plus 1, n plus 1, 3 to the 2n plus 2. So the limit of the absolute value of an plus 1 over an as n approaches infinity equals, what are we going to do with that? I have, watch what we do, an plus 1, we know it, it's n plus 2 times 5. I'm going to break that down to 5 to the n times 5 to the first, n plus 1, 3 to the 2n times 3 squared. And notice it's divided by an, right? Divided by an. So what I'm going to do instead of division, I'm going to do multiplication and flip an. N times 3 to the 2n divided by n plus 1 times 5 to the n. Is that okay? So here what we get, the 5 to the n cancels 5 to the n. 3 to the 2n cancels 3 to the n. And any constants I see, like the 5, you pull it out. 3 squared is 9. That's all I could pull out. Let's see what is left. N plus 2 over n plus 1 times n over n plus 1. When I pass the limit inside, let's see what we get. 5 over 9 times. The limit of this is 1. You could do L'Hopital, infinity or infinity L'Hopital, or you know the 1 in the front and 1 in the front. So 1 over 1, 1. Same thing with the other 1, 1. So we get 5 over 9, which is less than 1. Then it converges, so the given series converges by the ratio test. By the ratio test. we are going to recall, first thing, the absolute value of sine any function is always less than or equal to 1. Same thing for cosine. Cosine any function, we stated that before, less than or equal to 1. And we stated that the absolute value of arctangent of x is less than pi over 2. And also good to know that n is always bigger than natural log of n for n positive or bigger than 0. So to look at another example, let's look at this one, ln, 1 over ln times negative 1 to an nth power. Does this converge, diverge? What is it? Absolute conversion, condition conversion? We can try AST. So AST says, so this is an, 1 over ln of n. We need to find the limit of an as n approaches infinity. So limit of 1 over ln of n, that's infinity over, this goes to 0, right? And another thing you want to do is find an plus 1 to check if it's decreasing or not. So what do you think? A sub n plus 1 is less or bigger? It's less than, right? An. So then the way to check without a calculator if it's less or bigger, so you know an, which is 1 over ln, if you want to try to graph it, maybe graphically it will show you how that's going to look like. Another way, if you don't feel like, oh, I don't know if that's really what I'm looking for, you can find the derivative for that. So if you, or you can take f of x to be 1 over natural log of x, and then rewrite it natural log of x all to the negative 1. Then the derivative, bring the negative 1 down, natural log of x, negative 2 times the derivative of that. So it's negative 1 over x natural log of x squared. So you can see it's less than 0 in this case. So it's decreasing. So since the two conditions of the AST are met, then we can say that this series, or the absolute value of that, converges, right? So, so we can say the given series converges. So the given series, negative 1 to an n, 1 over natural log of n, converges by AST. So in 11.6, section 11.6, when we approach AST this, the procedure was always to start taking absolute value. That's how we did it. So you can, we take the absolute value of negative 1 to an n, 1 over natural log of n. And this would give us 1 over natural log of n, because the absolute value cancels the negative. Now, how do I check if this series converges or not? I'm not going to use AST here, because there's no alternating anymore. But we can go back to property 4 here that I wrote down there, that n is bigger than natural log of n, right? So I can start with that, n bigger than natural log of n. And then I'm going to flip both sides. So when you flip both sides, you change the inequality sign, because of the terms are positive. And then that tells me I can do the sum less than the sum of that. Notice the one on the left side diverges by p-test. This is a harmonic series. If the smaller diverges, the bigger one diverges by the comparison test. So these are the procedure from the previous section. When you take absolute value and it diverges, you check if it converges or not for the actual one, which we did. So we checked it out, it converges. So this means the given series now converges conditionally. Okay, let's look at this next one. Negative 1 to the k, arctangent of k over, let's say, k to the third, where k runs from 1 to infinity. Test if this converges, diverges, converges absolutely, or converges conditionally. So we're going to do the opposite value of negative 1 to the k times arctan. So the opposite value will clean up that negative thing, arctan of k over k cubed, right? So what's next? Like, how do I know if this converges or diverges? Well, we already told you earlier, one thing you can do, this is just arctangent of k over the opposite value of k cubed, which is k cubed. K is positive. Now, we know the top part is less than what? Pi over 2, right? So that's over k cubed. If you do sum arctan of k less than the sum of that, so the one on the right side converges by p-test. If the bigger one converges, the smaller must converge. So this one converges by comparison test. The bigger one converges, the smaller converges. So when I took the opposite value and I found it converges, then the given series what? The given series converges absolutely. And that's where we stop for that problem. If it diverges, you move on and then check AST and see if it converges or diverges. Next example, the sum of n squared e to the negative n cubed. N ranges from 1 to infinity. So it's not alternating here. So first we look at the p-test to use. It doesn't work. The geometric series test doesn't work. What's the next test you like to try? It's not the root test, right? You can eliminate them, cross them out on your list. Process of elimination. If we try the comparison test, I mean, maybe you want to go and say, okay, can I just do like this, rewrite it? Yeah, you can if you want. It would be difficult to use a comparison test, okay, and hence the limit comparison test. What's the next thing to try? If you want to try the ratio test, you're going to find an plus 1, which is n plus 1 squared e to the n plus 1 cubed. Right? So now, if you try to find the limit of as n goes to infinity of an plus 1 divided by, which I'm going to turn into times, it's going to give us this. Now, how are we going to find the limit? So we can take these together, that would be 1, but how about these? That would be like indeterminate, right? You're going to try to use L'Hopital's rule, maybe. But even with L'Hopital's rule, that's not going to get us that far. Because the drift to the top, what would be the drift of e to the n cubed? So what's the drift of e to the n cubed? That reminds us, if you have a number, say a to a function, the derivative for that is f prime of x times itself times natural log of the base. So if you want to find the derivative of this, that would be the derivative to the top 3n squared times itself times natural log of the base, which is 1. But still, it's not gonna, like, you're gonna get the same thing top and bottom. It's not gonna help that much. So I think the ratio test is not gonna be easy to use. What can be another? We said root test is you cross it out. We cross out. How about divergence test?
I use that.
Not,
It gives me like 0, so it's...
so we're left with only one test, the integral test. So the integral test, let me write that series again. E negative n cubed, n goes from 1 to infinity. So you're gonna say the conditions for the integral test, we need to list them out. So we're gonna verify or write down the things. So first we turn into a function, x squared e negative x cubed. That's our function. And then what do we say? So we say f is continuous and what? Positive, right? Positive over the interval 1 to infinity, because that's what the bounds are. And then we need to find the derivative for this to check if it's decreasing or not using the product rule. So 2x times the second one plus the first one times the derivative of the second one, which is negative 3x squared times itself. And after we do this, we're gonna try to simplify now. 2x over e to the x cubed minus 3x to the fifth over ex cubed. So 2x minus 3x to the fifth over ex cubed. What we can do is factor x on the top, 2 minus 3x to the fourth over ex cubed. So at some point here, remember that wait, this is square here. So at some point we're gonna have to check x1. If you put 1, you're gonna get 2 minus 3 in that's a negative 1. If you put 2, that's gonna be negative. Even the negative values is getting really smaller. So this one is less than 0 for all x bigger than or equal to 1. So that tells us it's a decreasing, right? So decreasing on the interval 1 to infinity. So we can apply the integral test. And how do we apply the integral test? We need to find the integral from 1 to infinity of x squared e negative x cubed dx. And to do that, we need to rewrite this as an improper, say like b goes to infinity, integral from 1 to b, x squared e negative x cubed dx. On the side, you can do the integral for this. I believe u sub will take care of it by taking u to be negative x cubed, and du is negative 3x squared dx. Assume everyone can integrate this. After we do the integration and all the substitution, we're going to get negative 1/3 e negative x cubed from 1 to b. So this one, if you find the limits for this, plug the values in first, e negative b cubed plus 1/3 e negative 1. E negative infinity, that's going to go to 0, so that would give us 1/3 e negative 1 or 1 over 3 over e. So that tells us it converges, right? So this one converges, hence the given series converges as well by the integral test. Okay, so when we look at something like this, students try it, so they found the conversion test works. So what that means, this is AK, is K times the square root of K squared plus 1. If you want to find BK, you drop the small terms like the plus 1, which this turns out to be K times K squared, right? So the right-hand side, so the BK converges, this one converges by the p-test. If I want to convert these two together, we know that 1 over k times the square root of k squared plus 1, the larger the denominator, the smaller the fraction. So AK is less than BK, right? If you do the sigma, so AK here is the left side, the right side converges, so the left side must converge by the comparison test. Next example, say sine because in all the examples we've done so far, we didn't show like sine or cosine. So how about sine 2n over 1 plus 2 to the n? Does it converge or diverge? So when I see sine or cosine, I try to take the absolute value because of one of the properties I showed you earlier, that the absolute value of sine, any function, or cosine is always less than or equal to 1. So if we do the absolute value on sine 2n over 1 plus 2 to the n, this would be less than or equal to 1 over 1 plus 2 to the n. Right? Because sine 2n absolute value is less than or equal to 1. Now the one on the right side, it might be a little bit difficult to decide if it converges or diverges. But doesn't hurt to also compare it to 1 over 2 to the n, right? Because the larger the denominator, the smaller the fraction. So the one on the right side now, I'm going to look at this. This is, if you plug in n1, n2, n3, you will see that's a geometric series. This is a GS with common ratio R 1/2, which is less than 1 and bigger than -1. So this one converges by, let's call the GST, geometric series test. If the bigger one converges, what happened to the smaller one? So then that thing, when we take the absolute value of it, now we say converges absolutely. And there's a theorem in the previous section, it says if a series converges absolutely, hence converges by one of the theorems. Sum three to the k minus 1 times 5 to the k plus 1 over k to the k. When I saw k to the k, something came to mind as the root test. So let's see. Let's do some rewriting. 3 to the k times 3 to the negative 1. 5 to the k times first to the first, k to the k. Now that 3 to the negative 1, you can pull it outside with the 5, so 5 over 3. All the other terms, 1, 2, 3 of them, they all have to the k power. So I could do it this way. Right, that's in return, this is 15 over k to the k power. Was limit of the square root of the absolute value of ak as k approaches infinity. So limit the kth root, k goes to infinity, 15 over k to the kth power. So the two k's will cancel each other. So we do limit as k goes to infinity, 15 over k, which is 0. This is less than 1. So it converges by the root test. Now, sometimes you can tell here, so this one converges, hence the given series converges by the root test. You can probably use a different test, doesn't mean you can only use one test that would work. Maybe different tests can work at the same time.